A brilliant jet of energy stretches across millions of light years, a cosmic beacon from an impossible engine. These are quasars, the hyperactive hearts of distant galaxies, and they are the most luminous objects in the known universe. Each one is powered by a supermassive black hole, a gravitational monster feasting on surrounding matter. By the end of this journey, you will understand 25 of their most mind-bending phenomena that defy the very laws of physics as we know them. We will explore how some appear to move faster than light and why others might hold the key to dark matter. How can an object brighter than 1 trillion suns remain one of cosmology's deepest puzzles? That brilliance is not just immense, it is fundamentally impossible by any standard we knew. A single quasar, a tiny pinprick in our telescopes, can outshine the combined light of every star in an entire galaxy. That is hundreds of billions of suns, all eclipsed by a single hyperactive core. How can something so compact produce such an apocalyptic amount of energy? The secret lies in a cosmic engine of terrifying efficiency, the supermassive black hole's accretion disk. Picture a whirlpool of gas and dust spinning at nearly the speed of light as it funnels toward the event horizon. This is not a gentle spiral. It is a chaotic, violent maelstrom where particles collide with unimaginable force, heating up to millions of degrees. In this inferno, the friction and gravitational pressure are so extreme that matter converts directly into pure energy. This process, converting mass to energy, is far more efficient than the nuclear fusion that powers stars. A star converts only about 0.7% of its fuel into energy. But a quasar's accretion disk can achieve a staggering efficiency of up to 40%. That means almost half the mass of a swallowed star is blasted across the universe as light and radiation. Consider the first quasar ever identified, known as 3C273. To early astronomers, it looked like a faint, unremarkable star in our own sky. But its true nature was revealed when they measured its distance. 3C273 is not a star at all. It is a beacon from over 2 billion light-years away, shining with the power of more than 4 trillion suns. A single object so far across the cosmos that we can see it with a backyard telescope. This impossible luminosity is the first great paradox of quasars, a warning that the universe operates on a scale of power we are only beginning to comprehend. That raw power is funneled into something even more bizarre, colossal jets that blast matter across the cosmos. From the poles of these active black holes, focused beams of plasma erupt, accelerating to nearly the speed of light. These are not gentle streams of light. They are fire hoses of raw energy, so powerful and focused that they can stretch for millions of light years, far beyond the visible edges of their own galaxy. Imagine a single beam so long it could cross the distance between our Milky Way and the Andromeda Galaxy dozens of times over. The physics required to create such a structure is almost beyond belief. Intense magnetic fields generated by the churning accretion disk act like a cosmic nozzle. They squeeze and collimate the superheated plasma, forcing it into two narrow, opposing jets that remain tightly focused across unimaginable distances. Without this magnetic confinement, the jet would simply dissipate into a cloud, a faint puff in the interstellar wind. But here, the fields are so immense that they sculpt a perfect, lethal beam. We see the proof in objects known as head-tail radio sources. These are galaxies where the jets are bent into long, graceful arcs like cosmic smoke blown by a strong wind. This happens when the galaxy is moving rapidly through the hot gas that fills a galaxy cluster. The jets stream out behind it, creating a tail that can be millions of light years long, a permanent record of the galaxy's journey through space. These jets are not just spectacular light shows. They are fundamental players in the evolution of the largest structures in the universe. The energy they carry is so vast that when a jet plows into the sparse gas between galaxies, it heats it, shocks it, and prevents it from cooling and collapsing to form new stars. In this way, a single quasar can dictate the future of an entire galaxy cluster, shutting down star formation on a scale that dwarfs our own local universe. This is intergalactic engineering on the most epic scale imaginable. These cosmic jets hold an even deeper layer of strangeness. Within them, astronomers have clocked blobs of plasma moving at impossible speeds, seemingly breaking the universe's ultimate speed limit. We see knots of bright material racing along the jet, performing a feat that should be forbidden, traveling faster than light itself. This is the illusion of superluminal motion, a breathtaking cosmic mirage born from simple geometry and the unshakable rules of special relativity. The trick lies in the angle and the incredible velocity of the material. Picture a single blob of plasma ejected from the quasar, hurtling towards us at 99.9% the speed of light. As it moves, it emits light continuously, like a firefly blinking on and off. The first flash of light it emits has a head start, but the blob itself is moving almost as fast as that initial flash of light. If the jet is pointed almost directly at Earth, the later light it emits has a much shorter distance to travel to reach our telescopes than the earlier light did. From our perspective, the blob appears to have nearly caught up to its own initial light pulse, making its motion across the sky seem impossibly fast. It is like a cosmic runner on a track where the finish line is your eye. If the runner is incredibly fast and the track is angled just right towards you, each subsequent step the runner takes is closer to you than the last. Your brain perceives the runner as having covered the distance between those steps almost instantaneously. In reality, no information or matter is breaking the light-speed barrier. It is a flawless trick of perspective, a cosmic sleight of hand where the actual speed and our line of sight conspire to create an impossible spectacle. This phenomenon has been observed in countless quasars, a constant reminder that in the high-energy theater of the universe, seeing does not always mean believing. At the heart of this cosmic tempest lies the ultimate engine of destruction and creation, a supermassive black hole. This is not merely an object, but a region where the laws of physics as we know them break down completely. Its immense mass, millions or even billions of times that of our Sun, warps the fabric of space and time so severely that it collapses into a point of infinite density, a singularity. Encasing this unknowable point is the event horizon, the point of no return. It is not a physical surface, but a gravitational boundary from which not even light can escape. Cross this threshold, and you are erased from the observable universe, your information lost forever to the singularity's grip. This central engine is the anchor for the entire chaotic system, its immense gravity the sole reason for the quasar's existence. Just outside this abyss, however, lies a zone of frantic activity that reveals the black hole's deepest secrets. This is the broad line region, a thick shroud of intensely hot gas clouds swirling at breathtaking speeds just beyond the accretion disk. We cannot see these clouds directly, but their light carries a distinct fingerprint, a set of emission lines that are impossibly wide and blurred. This blurring is the key. The gas is moving so fast, whipped around by the black hole's gravity, that the light from clouds moving toward us is blue shifted, while light from those moving away is red shifted. The combined effect smears a single, sharp line of color into a broad, fuzzy band. This Doppler broadening is a cosmic speedometer. By measuring the width of these blurred lines, astronomers can calculate the velocity of the orbiting gas. And since that velocity is dictated by the gravitational pull of the central black hole, we can perform a remarkable piece of cosmic detective work. The speed of the gas directly reveals the mass of the invisible monster controlling it. This is how we weigh supermassive black holes across the universe, by reading the frantic signatures of the gas they hold captive. The broad line region is a screaming witness to the power of the singularity, its blurred light a direct message about the nature of the abyss it orbits. This thick shroud of gas, the broad line region, is just the inner layer of a much larger structure. Encasing the entire central engine is a colossal donut of dust and gas known as the obscuring torus. From our perspective on Earth, this simple shape dictates everything we see. If we happen to be looking face-on down the barrel of the jets, we have a clear, direct view of the brilliant accretion disk and the broad line region. We classify this as a brilliant, unobscured quasar. But if our view is from the side, peering through the dense wall of the torus, the story changes completely. The visible light from the accretion disk is utterly blocked by light years of dust, leaving only the faint, longer wavelength radio waves from the jets to slip through. The same ferocious engine appears to us as a dim, quiet galaxy, its true nature hidden behind a cosmic veil. This single structure, the torus, explains why the same fundamental object can appear in two completely different guises across the universe. Yet sometimes this cosmic veil seems to lift or drop before our very eyes. Astronomers have witnessed a bizarre class of objects known as changing-look active galactic nuclei. Over mere months or years, a brilliantly shining quasar will dramatically fade, its broad emission lines vanishing as if a switch has been flipped. Then, just as mysteriously, it might roar back to life. This is not a trick of the light, but a real transformation happening on a human timescale. The leading theory points to a fickle appetite. The central black hole's feast of gas might suddenly be cut off, perhaps by a passing star being torn apart and briefly fueling a brilliant flare before the famine returns. Alternatively, a thick, wandering cloud of dust within the torus could drift directly into our line of sight, momentarily blocking our view of the central fire. These changing-look quasars are cosmic chameleons, revealing that the violent processes at the hearts of galaxies are far more dynamic and unpredictable than we ever imagined. This unpredictable energy does not just create a light show, it holds the power of life and death over entire galaxies. The concept is known as quasar feedback, and it is one of the most profound forces shaping galactic evolution. During its most active phase, a quasar blasts out unimaginable amounts of radiation and powerful winds. These winds can slam into the vast reservoirs of cold gas throughout the host galaxy, the very raw material needed to form new stars. The effect is like using a cosmic blowtorch on a cloud of interstellar hydrogen, heating it and pushing it away with such force that it can never collapse again. This process effectively sterilizes the galaxy, halting the birth of new stars and sealing its fate. A galaxy that might have continued forming stars for billions of years is instead left to age passively, its stellar population slowly reddening and fading. This violent self-regulation solves a great cosmic mystery. It explains why we do not see galaxies with the immense sizes and masses that their vast gas reserves should have allowed. The quasars within them, in their brilliant, furious youth, blew out the candles before too many stars could be lit. The most luminous objects in the universe are not just beacons, they are cosmic guardians, enforcing a balance that has shaped the galaxies we see today. That brilliant light, a beacon from the early universe, carries a hidden code in its very color. The light from the most distant quasars is stretched, shifted far into the red part of the spectrum. This redshift is the universe's own fingerprint, a permanent record of its relentless expansion. As space itself stretches during the light's multi-billion-year journey, the light waves are stretched along with it, their wavelength growing longer and redder. The further the light travels, the more stretching it endures and the greater its redshift becomes. This simple, profound relationship is the Hubble law, the cornerstone of modern cosmology. It means that by measuring a quasar's redshift, we can directly calculate its distance. The most extreme redshifts place these objects at the very edge of the observable universe, so far away that their light has been traveling for over 13 billion years to reach us. We are not just looking across space, we are gazing back in time. When we observe a high redshift quasar, we see it not as it is today, but as it was when the universe was a fraction of its current age, a turbulent and formative era. These objects are true cosmic time machines. Their light left its source before our own planet even existed, carrying a pristine snapshot of the early cosmos. In their brilliant, furious hearts, we witness the adolescence of galaxies, a time when supermassive black holes were actively growing and shaping the universe around them. They reveal a period of intense violence and construction, a chapter of cosmic history that would otherwise be completely lost to us. This ability to see across such vast stretches of time raises a fundamental question. Are we seeing a true representation of the early universe, or is something else distorting our view? This cosmic time machine holds a further secret, a way to see the invisible. The brilliant light of a distant quasar can be warped and magnified by the gravity of any object that drifts directly between it and our telescopes. This is the magic of gravitational microlensing, a natural telescope powered by Einstein's theory of relativity. The gravity of the intervening object, whether a star, a planet, or something else, acts as a tiny lens bending the fabric of space around it. As this lens moves across our line of sight, it briefly focuses the quasar's light, causing the faraway beacon to flicker and brighten in a very specific way. This is not a random twinkle, it is a precise signature. The duration and shape of the brightening tell us the mass of the invisible object causing the lensing effect. It is a cosmic scale, weighing things we cannot see by the distortion they imprint on a beam of light billions of years old. Astronomers use these chance alignments to take a census of the dark, compact population within entire foreground galaxies. They have found countless rogue planets orphaned from their solar systems and drifting in the interstellar void. They have detected faint, cold stars that would otherwise be lost in the glare of their own galaxy. But the hunt goes deeper into the greatest mystery of modern cosmology, the hunt for dark matter. One leading candidate for this unseen mass was a class of objects known as MACHO, an acronym for Massive Astrophysical Compact Halo Objects. These would be dark, hefty bodies like black holes, neutron stars, or brown dwarfs, swarming in the vast halos of galaxies. For years, microlensing surveys meticulously monitored millions of stars in nearby galaxies, watching for the telltale brightening that would signal a MACHO drifting in front. The results were profound, but not as expected. While some MACHO were found, their numbers were far too few to account for the immense gravitational pull we attribute to dark matter. The mysterious substance shaping the cosmos is not made of these compact stellar remnants. The flickering light of quasars has spoken, ruling out a major possibility and pushing the search for dark matter into even more exotic and elusive realms. This brilliant light, as it journeys for billions of years, does not travel through an empty void. It passes through a complex, invisible architecture that leaves its own unique mark. When we split the light from a distant quasar into its constituent colors, we find something astonishing. The pristine, continuous spectrum is slashed with thousands upon thousands of dark lines, a dense thicket of missing light that astronomers call the Lyman-alpha forest. Each one of these lines is a tiny bite taken out of the quasar's brilliance, a specific fingerprint of a single cloud of neutral hydrogen gas. These are not clouds within the quasar's own galaxy. They are the ghostly, primordial material floating in the vast expanses between galaxies, each one at a different distance from us. As the quasar's light passes through each cloud, the hydrogen atoms within it are tuned to absorb one very specific color of ultraviolet light, known as the Lyman-alpha line. But because each cloud exists at a different point in the expanding universe, the space between us and it has stretched to a different degree. The light that left the quasar as a single, precise color is stretched to a longer, redder wavelength by the time it reaches a nearby cloud, and stretched even more by the time it reaches a cloud farther away. From our perspective, the single Lyman-alpha absorption line is stamped onto the spectrum at 1,000 different positions, each one corresponding to a different hydrogen cloud at a different redshift. The result is not a single line, but a veritable forest of them, a dense collection of absorption features that grows thicker and more complex the farther back in time we look. This forest is far more than a curiosity. It is one of the most powerful tools we have for mapping the invisible skeleton of the cosmos, the cosmic web. The distribution of these hydrogen clouds is not random. They trace out the faint, filamentary structure of dark matter upon which all visible matter is built. Where the lines cluster densely, we are looking through a dense knot in the web, a proto-cluster of galaxies. Where the lines are sparse, we are peering into a vast, empty cosmic void. By analyzing the intricate pattern of this forest in a single quasar spectrum, astronomers can reconstruct a one-dimensional slice through the universe's large-scale structure, a core sample of the cosmos itself. It is as if the quasar's light is a brilliant probe, illuminating every single wisp of gas along its path and delivering a perfect map of its billion light-year journey directly to our telescopes. Sometimes the violence of a galaxy merger leaves behind a double signature at the heart of the new system. We are now finding evidence that some active galactic nuclei may be powered not by a single gravitational monster, but by two locked in a tight orbital dance. These binary supermassive black holes are the predicted end result of galaxies colliding and merging. When two galaxies smash together, their central black holes eventually sink to the new core through a process called dynamical friction, and they can begin to orbit one another. This creates a system of unimaginable power and complexity. The telltale signs of such a cosmic duet are subtle but distinct. Astronomers search for quasars whose light output pulses with a regular, repeating rhythm. This periodic flickering could be caused by the orbital motion of the two black holes. As they swing around each other, their gravitational tug can periodically disrupt the flow of gas in their shared accretion disk, causing bursts of infalling material and a corresponding flare of brightness with each orbit. Another clue lies in the jets. If one of the black holes is ejecting a jet, the gravitational pull of its companion can cause the jet to wobble or precess, much like a spinning top slowly tracing a circle on a table. This precession would make the jet's apparent direction in the sky change over time, a slow cosmic gyration that points directly to an unseen gravitational partner. The ultimate fate of such a binary is a cataclysmic merger. As the two black holes spiral closer, they lose energy by rippling the very fabric of spacetime itself, emitting gravitational waves. While we have detected the high-frequency chirps from stellar mass black hole mergers, the universe should be filled with a low, deep hum from countless supermassive binary systems. This is the gravitational wave background, a perpetual symphony of spacetime vibrations from merging giants across the cosmos. This faint signal has so far eluded our detectors, but a new era of observation is dawning. The upcoming Laser Interferometer Space Antenna, or LISA, is a mission designed specifically to listen for these low-frequency waves. Once operational, it will tune into this cosmic hum, transforming our indirect evidence for binary black holes into direct, irrefutable confirmation. We will finally hear the universe's background music, a chorus composed by the slow, inevitable dance of the cosmos's most powerful engines. This elegant idea that all quasars are fundamentally the same is known as the unified model. It argues that the wild variety we observe, from brilliant quasars to faint radio galaxies, is not a difference in the engine itself, but a simple matter of perspective. Our viewing angle is the cosmic stage director, controlling the entire performance we witness. Look directly down the open pole of the system, past the obscuring torus and straight into the fiery heart, and you see a blazar, a violently variable object where the jet is aimed right at you. Tilt your view just slightly, so you still have a clear line of sight to the accretion disk, but are no longer staring directly into the jet's barrel, and you observe a classic, brilliant quasar. Now shift your perspective to the side, looking directly through the thick, dusty wall of the torus. The visible light from the central engine is completely blocked, leaving only the faint radio glow of the jets to be seen from the side, and you are now looking at a radio galaxy. The same object, the same physics, but three completely different cosmic identities, all defined by a single, simple angle. The evidence for this model is compelling. We see the same types of host galaxies for these different classes of objects, and the estimated masses of their central black holes fall into the same colossal range. It is a beautifully simple and powerful framework for organizing the chaos of the cosmos. Yet, as with all things in astronomy, the universe loves to throw us curveballs. There are glaring exceptions that refuse to fit neatly into this unified picture. Some active nuclei appear to have the wrong type of jets for their orientation, or they possess obscuring tori that are far too thin or patchy to match the model's predictions. The most telling anomalies are the changing look quasars we discussed earlier. How can an object change its fundamental type in just a few months? If the unified model were solely about a fixed, physical structure like a torus, such a rapid transformation from a bright quasar to a hidden nucleus would be nearly impossible. A solid torus of dust and gas simply cannot form or disappear on such a short timescale. This forces us to consider a more dynamic and messy reality. Perhaps the torus is not a smooth, stable donut at all, but a chaotic, clumpy fog of clouds constantly shifting and reforming. Maybe the primary factor is not a permanent structure, but the black hole's immediate appetite. A sudden famine of infalling gas could cause the entire brilliant accretion disk to vanish, effectively turning off the central engine regardless of our viewing angle. The unified model is not wrong. It is a brilliant and essential starting point, a map of the territory. But the true landscape of these active hearts is far more complex, a place where fixed structures and volatile processes intertwine, forever challenging our desire for simple cosmic categories. This brilliant light, as it journeys for billions of years, does not travel through an empty void. It passes through a complex, invisible architecture that leaves its own unique mark. When we split the light from a distant quasar into its constituent colors, we find something astonishing. The pristine, continuous spectrum is slashed with thousands upon thousands of dark lines, a dense thicket of missing light that astronomers call the Lyman-alpha forest. Each one of these lines is a tiny bite taken out of the quasar's brilliance, a specific fingerprint of a single cloud of neutral hydrogen gas. These are not clouds within the quasar's own galaxy. They are the ghostly, primordial material floating in the vast expanses between galaxies, each one at a different distance from us. As the quasar's light passes through each cloud, the hydrogen atoms within it are tuned to absorb one very specific color of ultraviolet light, known as the Lyman-alpha line. But because each cloud exists at a different point in the expanding universe, the space between us and it has stretched to a different degree. The light that left the quasar as a single, precise color is stretched to a longer, redder wavelength by the time it reaches a nearby cloud, and stretched even more by the time it reaches a cloud farther away. From our perspective, the single Lyman-alpha absorption line is stamped onto the spectrum at 1,000 different positions, each one corresponding to a different hydrogen cloud at a different redshift. The result is not a single line, but a veritable forest of them, a dense collection of absorption features that grows thicker and more complex the farther back in time we look. This forest is far more than a curiosity. It is one of the most powerful tools we have for mapping the invisible skeleton of the cosmos, the cosmic web. The distribution of these hydrogen clouds is not random. They trace out the faint, filamentary structure of dark matter upon which all visible matter is built. Where the lines cluster densely, we are looking through a dense knot in the web, a proto-cluster of galaxies. Where the lines are sparse, we are peering into a vast, empty cosmic void. By analyzing the intricate pattern of this forest in a single quasar spectrum, astronomers can reconstruct a one-dimensional slice through the universe's large-scale structure, a core sample of the cosmos itself. It is as if the quasar's light is a brilliant probe, illuminating every single wisp of gas along its path and delivering a perfect map of its billion light-year journey directly to our telescopes. This speed of creation presents a monumental puzzle. How could such gravitational behemoths with masses billions of times that of our Sun assemble in less than 1 billion years? The formation of the very first quasars defies our standard models of black hole growth. We know how stellar mass black holes form from the collapse of massive stars. But that process is slow. A star lives for millions of years before it dies, and the resulting black hole is small, perhaps only 10 or 20 times the mass of the Sun. For it to grow into a supermassive monster, it would need to feast on gas at a ferocious, sustained rate, pushing against the very theoretical limits of how fast a black hole can consume matter. It seems almost impossible for a stellar seed to grow that big, that fast, so cosmologists have proposed a more dramatic birth for these primordial giants. One compelling theory is the concept of direct collapse. Imagine a pristine cloud of hydrogen and helium, one of the first structures to form in the early universe. Under the right conditions, this cloud could avoid fragmenting into many smaller stars. Instead, it would collapse as a single, monolithic entity, a cosmic catastrophe bypassing the star formation stage entirely. This direct collapse would create a black hole seed of immense proportions, not 20 solar masses, but perhaps 10,000 or even 100,000 solar masses right from the start. This colossal seed gives the black hole a huge head start, allowing it to reach supermassive status within the tight time frame allowed by our observations of the early universe. Another possibility involves a crowded stellar nursery. In the dense core of an early galaxy, massive stars could have formed and died in rapid succession, their black holes merging together and sinking to the center to form a single large seed. This is a bottom-up approach, building a giant from many smaller pieces. Yet another, more exotic idea suggests that the seeds could be primordial black holes, created not from stars but from extreme density fluctuations in the very first moments after the Big Bang. These would be fossils from the birth of the cosmos itself, wandering the universe until they found a galaxy to call home and began their feast. Each of these theories has its own challenges. The direct collapse model requires very specific, pristine conditions that may have been rare. The stellar merger scenario needs incredibly dense star clusters to work efficiently. The existence of primordial black holes remains entirely speculative. The truth is, we still do not know which path, or perhaps which combination of paths, nature chose. The existence of these early quasars is a glaring clue, a sign that our understanding of the universe's first chapters is still profoundly incomplete. They stand as cosmic stopwatches, their immense ages ticking down the time we have left to solve one of the greatest formation mysteries in all of cosmology. This flickering is not a flaw in the cosmic signal, but a feature we can use to our advantage. Quasars are not steady beacons, their light dances and shifts in unpredictable ways, brightening and fading over days, weeks, or even years. This inherent variability is the key to a brilliant technique known as reverberation mapping, a form of cosmic echolocation that lets us measure the unmeasurable. The process begins with a flare of intense light from the very inner edge of the accretion disk. This surge of high-energy radiation, called the continuum, races out in all directions at the speed of light. A short time later, astronomers notice a corresponding change in the broad emission lines, the blurred fingerprints of the fast-moving gas clouds in the broad line region. The key is the delay. That light pulse from the disk had to travel the extra distance out to the gas clouds, excite their atoms, and then the new light from those clouds had to travel all the way back to our telescopes. The time gap between the continuum flare and the response in the emission lines is a direct measure of the distance between the accretion disk and the broad line region. It is a simple principle of physics. Distance equals the speed of light multiplied by the time delay. By carefully monitoring these cosmic echoes, we can literally map the geometry of this violent, invisible zone. We have learned that the broad line region is not a perfect sphere, but often a flattened, disk-like structure itself, with different clouds orbiting at different distances. Reverberation mapping turns the quasar's own flickering heart into a precision ruler, allowing us to chart the architecture of chaos itself and weigh the central black hole with remarkable accuracy, all from the timing of a distant flash of light. This relentless cosmic acceleration finds its ultimate expression in the most energetic particles ever detected, messengers from the deepest voids. Occasionally, our planet's atmosphere is struck by a single subatomic particle carrying the kinetic energy of a professionally thrown baseball, all compressed into a speck smaller than an atom. These are ultra-high energy cosmic rays, and their existence pushes the limits of what we believe is possible in the universe. They travel at a fraction of a percent below the speed of light, and their origin has been one of astrophysics' most enduring puzzles. What natural particle accelerator could possibly be this powerful? The leading suspects are the very engines we have been exploring, the relativistic jets erupting from active galactic nuclei. Within those magnetic tornadoes, conditions are so extreme that protons and atomic nuclei can be boosted to energies millions of times greater than anything achievable in our most powerful particle colliders on Earth. These jets could be the ultimate cosmic cannons, firing bullets of pure energy across the intergalactic medium. Yet this journey is not without peril. The universe itself places a fundamental speed limit on these travelers. Theorists Greisen, Zatsepin, and Kuzmin calculated that the vast expanses of space are not truly empty. They are filled with the faint, relic radiation from the Big Bang, a cosmic microwave background that permeates all of creation. A proton traveling from a distant quasar with its unimaginable energy would eventually collide with one of these serene, low-energy background photons. From our perspective, that microwave photon would be harmless, but for a proton moving at near light speed, that photon is transformed. It is massively blue-shifted, becoming a blast of high-energy gamma radiation. When the proton smashes into this now deadly photon, the collision is so violent it creates new particles, sapping the proton's energy. This process acts like a cosmic friction, a gradual braking system over long distances. The result is the GZK cutoff, a theoretical upper limit on the energy that a cosmic ray can retain if it comes from a source more than a few 100 million light-years away. Beyond that distance, the cumulative collisions should erode its energy, preventing the very highest energy particles from ever reaching us. This is where the mystery deepens. Our detectors on Earth have, in fact, recorded a handful of these ultra-high energy events, particles that seem to have beaten the GZK cutoff. How is this possible? Either these cosmic rays come from relatively nearby sources within our local cosmic neighborhood, or our understanding of particle physics needs revision. This is where the brilliant jets of active galaxies become prime suspects. A nearby quasar or a radio galaxy with its jet pointed in our general direction would be a perfect candidate, a local accelerator capable of firing the ultimate energy bullet without it being completely eroded by the long journey. The hunt to pinpoint the source of these rare events is a grand cosmic detective story, connecting the faint flicker of a distant galactic core to a tiny, catastrophic splash in our own sky. This chaotic zoo of quasars and active galaxies, with its chameleons and giants, was once a baffling menagerie. Astronomers needed a way to bring order to the chaos, to find a simple pattern behind the wild diversity. They found it in the quasar main sequence, a powerful framework that does more than just label these objects. It reveals the fundamental engines driving their immense power. Think of it not as a simple checklist, but as a cosmic map. This map has two primary coordinates that determine a quasar's entire personality. The first is the accretion rate, which is essentially the black hole's appetite. How quickly is it devouring the gas from its surrounding disk? The second is our old friend, the viewing angle. Are we looking face on, edge on, or somewhere in between? These two factors, working in concert, dictate whether we see a brilliant blue quasar, a reddened, dust-obscured giant, or something in between. A black hole feasting at a high rate with a high accretion rate produces a hotter, bluer accretion disk. If we have a clear view of this vigorous engine, we classify it as a blue, luminous quasar. But if that same ravenous black hole is hidden behind its dusty torus, we see it as a red quasar, its brilliant blue light absorbed and re-radiated as longer, redder wavelengths by the intervening dust. On the other hand, a black hole on a starvation diet with a very low accretion rate has a much fainter, cooler disk. Its appearance is less about the dazzling central fire and more about the structure of the surrounding low-energy gas. This elegant sequence transforms a bewildering collection of oddities into a coherent family tree. It moves us beyond simply asking, what does this object look like? It allows us to ask the deeper physical question, what is this object actually doing? The quasar main sequence is the key that unlocks the underlying physics, showing us that the wild variety in the cosmos is governed by a few simple, powerful rules. Every so often, a galaxy's silent heart awakens with a sudden, terrifying flash. This is a tidal disruption event, a cosmic cataclysm where a star's simple orbit becomes a death spiral. When a star drifts too close to a supermassive black hole, it crosses a point of no return known as the tidal radius. Here, the gravitational pull on the side of the star nearest the black hole is catastrophically stronger than the pull on the far side. This difference, the tidal force, stretches the star horizontally while compressing it vertically, pulling it apart into a long, thin stream of superheated gas. The star is not swallowed whole. It is shredded, its material stretched into a luminous arc that wraps around the black hole in a chaotic, swirling stream. For a brief, brilliant period, this stream of stellar debris creates a miniature imitation of a quasar. As the gas from the torn-apart star falls back toward the black hole, it forms a temporary, incredibly hot accretion disk. The friction and collisions within this disk heat it to millions of degrees, generating an intense flare of radiation that can outshine the combined light of every star in its host galaxy. We see a quiet, normal galaxy suddenly ignite with the fury of a quasar, a beacon of violent rebirth. Yet this is a transient spectacle. Unlike a true quasar, which is fed by a steady reservoir of gas, this flare is powered by a single stellar meal. Within months or a few years, the scattered debris is either consumed or blown away, and the brilliant flare fades, leaving the galactic core dormant and silent once more. This fleeting violence offers astronomers a precious gift, a chance to study dormant black holes. In a quiet galaxy with no active nucleus, the central supermassive black hole is invisible, hidden by its own lack of activity. A tidal disruption event acts like a flashbulb in a dark room, momentarily illuminating the hidden monster at the center. By analyzing the light curve of the flare, how it brightens and then fades, scientists can measure the mass of the black hole itself. The duration and peak of the flare are directly tied to the gravity of the central object. These events are natural experiments, allowing us to take a census of the sleeping giants in galaxies all around us, confirming that nearly every large galaxy harbors one, even when it gives no other sign. It is a stark reminder that the calmest-looking galaxy can hide a ferocious potential, a power that only reveals itself in moments of celestial destruction. This cosmic hierarchy of black holes holds a glaring and puzzling gap. we have discovered plenty of stellar mass black holes, the remnants of dead stars, typically weighing between 5 and 100 times the mass of our Sun. And we know supermassive black holes, the monsters at the center of nearly every large galaxy, with millions or even billions of solar masses. But what lies in between? The universe seems to be missing its middleweights, the intermediate mass black holes that should logically bridge these two extremes. Finding them is crucial, as they could be the missing link, the seeds from which the supermassive giants grew. So where are they? One promising hunting ground is within the hearts of smaller galaxies. A brilliant classic quasar requires a supermassive engine, but a lower luminosity active galactic nucleus, shining with just a faint whisper of the power, could very well be driven by an intermediate mass black hole on its way to becoming a true giant. Another clue comes from a bizarre and incredibly bright class of events known as ultra-luminous X-ray sources, or ULCs. These are points of intense X-ray light located far from the centers of their host galaxies out in the spiral arms. Their luminosity is so great that it pushes the theoretical limits for a stellar mass black hole. Could these be intermediate mass black holes weighing a few thousand suns caught in the act of a violent feeding frenzy? The evidence is tantalizing but contentious. Some ULXs might instead be ordinary stellar black holes with beams of radiation focused directly at us, creating an illusion of greater power. The hunt has also led scientists to the dense, ancient globular clusters that orbit our own galaxy and others. These swarms of millions of stars are prime real estate for black hole mergers and growth. Here, gravitational wave astronomy offers a new way to listen for these elusive objects. The mergers of black holes in the intermediate mass range would produce a distinct low-frequency chirp, a sound that detectors like LISA are being built to hear. Confirming the existence of these middleweights would do more than just fill a gap in a catalog. It would validate our entire story of how the universe builds its largest structures from the smallest beginnings. The search for the missing middleweight is a search for a cosmic stepping stone, a fundamental chapter in the life story of every supermassive black hole that now sleeps at the heart of a galaxy. Deep within the X-ray glow of an active nucleus lies a single, distorted fingerprint. It is the spectral signature of iron atoms, but it looks nothing like the sharp, clean line you would see in a laboratory. This iron emission line is profoundly broadened and skewed, stretched into a lopsided curve that tells a tale of spacetime itself being twisted into knots. The cause of this distortion is a brutal combination of two relativistic effects, both occurring just outside the point of no return. First, consider the Doppler shift. The iron atoms are embedded in the inner accretion disk, whirling around the black hole at a significant fraction of light speed. The gas on the side spinning toward us has its light blue shifted to higher energies, while the gas spinning away has its light red shifted to lower energies. This smears the single, precise line into a broad, fuzzy band, but the true strangeness comes from general relativity. The immense gravity of the black hole acts like a cosmic anchor, dragging space-time around with it. This frame-dragging effect twists the inner disk into a final, frantic orbit. Most critically, the gravitational field causes a powerful redshift. Photons of light fighting their way out of this deep gravitational well lose energy, their wavelengths stretched and reddened. The final, bizarre shape of the iron line is a composite of these forces. The blue shifted peak from the approaching side of the disk is sharp and high. The red shifted tail from the receding side, amplified by gravity's relentless pull, is stretched out into a long, low, mournful slope. This is not a symmetrical smear, but a distinctly lopsided profile, a direct imprint of the black hole's spin and the extreme warping of space. By meticulously modeling this skewed line, astronomers can perform an almost miraculous feat. They can map the very inner edge of the accretion disk, determining exactly how close to the event horizon stable orbits can even exist. This, in turn, measures the black hole's spin, A maximally spinning black hole drags the inner disk so close that the ion line is skewed to its most extreme profile. A static black hole allows the disk to sit farther out, producing a milder distortion. This single, anomalous line is therefore one of our most powerful tools. It allows us to test the predictions of general relativity not in the mild gravitational fields of our solar system, but in the most violent environment possible, a place where space and time are stretched to their absolute limits. It is a direct look into the heart of the maelstrom, a confirmation written in twisted light that Einstein was right about the universe's most extreme architecture. This strange inverse relationship is known as the Baldwin effect. In the brilliant light of a quasar's spectrum, certain emission lines, like a signature from carbon atoms, behave in a counterintuitive way. The more luminous the quasar becomes, the weaker these specific lines appear. It is as if the brighter the central fire burns, the fainter its own shadow grows. This is not a flaw in the data, but a fundamental clue about the inner workings of these engines. One leading explanation points to a change in the ionization parameter. Think of the quasar's core as an ultraviolet lamp and the surrounding gas clouds as a screen. The ionization parameter is essentially the intensity of that lamp falling on the screen. In a lower luminosity quasar, the lamp is dimmer and the gas clouds are relatively dense. The ultraviolet light ionizes the outer layers of these clouds, creating a specific emission line. But in an incredibly luminous quasar, the lamp is so ferociously bright that it completely overwhelms the same clouds. The intense radiation doesn't just ionize the surface, it punches straight through, ionizing the entire cloud to a much deeper level and even blowing some of the gas away. This over-ionization changes the physics inside the cloud, making it less efficient at producing that particular carbon emission line. The line weakens not because the gas is gone, but because it has been transformed by the sheer power of the light. Another theory suggests the problem isn't just the lamp's brightness, but the color of its light. Perhaps the most luminous quasars have a different shape to their ionizing spectrum, producing more of the very high-energy photons that over-ionize carbon, effectively shutting down the production line for that specific fingerprint. The Baldwin effect is more than a cosmic curiosity, it is a diagnostic tool. By measuring how these lines weaken with increasing luminosity, astronomers can peer into the physical conditions of the broad line region across the entire quasar population. It reveals that the environment around a modest black hole is fundamentally different from that around a ravenous, ultra-luminous giant. The gas clouds are either denser, closer, or made of different stuff entirely. This subtle relationship, written in the fading strength of a spectral line, helps us classify quasars not just by how bright they are, but by the intricate physics of the maelstrom that surrounds them. This subtle alignment of distant quasars hints at a far grander, more unsettling cosmic pattern. Deep within the faint, cold glow of the cosmic microwave background, the afterglow of the Big Bang itself, astronomers have found a mysterious fingerprint they call the axis of evil. This is not a malevolent force, but a statistical anomaly, an unexpected alignment of hot and cold spots in the primordial radiation that seems to define a preferred direction in space. It is as if the infant universe was not perfectly uniform, but had a slight spin or tilt imprinted on its very fabric. The controversy erupts when we connect this to the quasars. Some studies have analyzed the rotation axes of the supermassive black holes powering these active nuclei, inferred from the direction of their powerful jets. Astonishingly, over billions of light years, these spin axes appear to show a correlation, a tendency to align with each other and, even more bizarrely, with the same cosmic axis of evil. If this is true, the implications are staggering. It would challenge the cosmological principle, the foundational idea that the universe is homogeneous and isotropic, meaning it looks the same in all directions and has no center or edge. This principle is the bedrock of modern cosmology, the assumption that allows us to apply the same physical laws everywhere. A preferred direction on the largest imaginable scales would shatter that assumption, suggesting the universe has a fundamental architecture we have not yet begun to comprehend. Could the initial conditions of the Big Bang have imprinted a universal spin, a faint vortex on the cosmos that guided the growth of supermassive black holes? Or does this point to something else entirely, a pre-Big Bang geometry or an influence from beyond our observable universe? The data remains contentious, with many scientists arguing it is a statistical fluke, a pattern we are imposing on random noise. Yet the mere possibility forces us to confront a profound question. Does the cosmos truly have no favorite direction, or are we just beginning to perceive its grand and perhaps lopsided design? Occasionally, the most profound discoveries are not things we see, but things we learn to illuminate. This is the story of dark galaxies, ghostly islands in the cosmic sea that were completely invisible until a brilliant celestial flashlight switched on. These are not galaxies as we know them. They are vast primordial reservoirs of hydrogen gas, the raw material for building stars, yet they have mysteriously failed to ignite. They are cosmic stillbirths, holding all the ingredients for a stellar population but remaining shrouded in darkness with only a handful of infant stars. For decades, they were a theoretical prediction, a missing piece in our models of galaxy formation, utterly undetectable by any telescope because they emitted almost no light of their own. The breakthrough came from a cosmic coincidence, a perfect alignment between our telescopes, one of these dark ghosts, and a distant quasar. The quasar's intense beam of ultraviolet radiation acted like a cosmic blacklight sweeping across the void. When this high-energy light struck the hydrogen atoms in the dark galaxy, it excited them, causing the gas to fluoresce with a very specific, faint glow. This is not the galaxy shining on its own, but rather, its cold gas being painted with light from an external source, a process similar to how a blacklight makes certain inks and fabrics glow in a dark room. This specific fluorescent glow is known as the Lyman-alpha line, and it appears as a faint, extended smudge around the quasar, a ghostly halo revealing the silhouette of a galaxy that should not be visible. The first confirmed dark galaxy was found this way, a vast cloud of hydrogen with less than 1% of the stellar mass of our own Milky Way, a failed giant illuminated only by its brilliant neighbor. This technique, called fluorescence mapping, has since revealed an entire hidden population. It suggests that the early universe was teeming with these dark, gaseous protogalaxies, objects that, for reasons we do not fully understand, never managed to collapse their gas and form stars in significant numbers. Perhaps their dark matter halos were too small to gather and compress the gas effectively. Maybe internal turbulence or feedback from those few early stars prevented the rest from coalescing. Whatever the reason, their discovery solves one mystery while creating another. We now know these dark building blocks exist, but we must ask why so many never graduated to become the brilliant galaxies that now light up the cosmos. They are the silent majority of the early universe, and without the accidental flashlight of a quasar, their profound presence would have remained a cosmic secret forever. This challenge to cosmic uniformity reaches its ultimate expression in the discovery of an object so large it should not exist at all. Astronomers have mapped a structure known as the huge LQG, an immense grouping of 73 quasars all bound together by gravity. This is not a simple cluster, but a cosmic continent stretching an almost incomprehensible 4 billion light-years across its longest dimension. To grasp that scale, consider that the entire span from our Milky Way to the most distant observable galaxies is only about 93 billion light-years. This single structure occupies a significant fraction of the known universe. Its sheer size directly confronts one of the most sacred principles in all of cosmology. The cosmological principle states that on the largest scales, the universe is homogeneous and isotropic. This means that no matter where you are or which way you look, the cosmos should appear roughly the same, with matter evenly distributed like raisins in a vast, expanding loaf of bread. There is a theoretical upper limit to how big any structure should be able to grow before it dissolves into this uniform background, a limit calculated to be around 1.2 billion light-years. The huge LQG shatters that limit, its 4 billion light-year length implying a lumpiness to the cosmos that our fundamental models simply do not allow. The debate this discovery sparked was immediate and intense. Is this colossal grouping a real structure, or is it a statistical phantom, a chance alignment of quasars that only looks like a connected group from our particular vantage point? Could our methods for measuring such vast distances be introducing a subtle error that makes these separate objects appear linked when they are not? If it is real, then our standard model of cosmology, the very foundation of how we understand the universe's evolution and composition, requires a serious revision. We may need to consider exotic new physics, perhaps involving dark energy or the primordial conditions of the Big Bang itself, that would permit such titanic structures to form. The huge LQG stands as a monumental question mark etched across the sky, a pattern of brilliant beacons that either reveals a profound new truth about cosmic architecture or highlights the limits of our own perception. These cosmic puzzles, from ghostly dark galaxies to structures of impossible scale, will soon face the scrutiny of a new era of observation. The next generation of telescopes, instruments of unprecedented power, are poised to transform our view of these brilliant monsters. The James Webb Space Telescope, with its infrared eyes, is designed to peer through cosmic dust and look further back in time than ever before. It hunts for the very first quasars, the primordial seeds that ignited when the universe was a mere infant. Finding them would be like discovering the first spark that started a cosmic fire, revealing the conditions that allowed such giants to form so quickly after the Big Bang. Meanwhile, on the ground, the Vera C. Rubin Observatory will conduct a relentless, decade-long movie of the entire southern sky. Its immense camera will capture the flickers and flares of billions of celestial objects, catching quasars in the act of transformation. It will find thousands of tidal disruption events, those sudden stellar shreddings, and track the subtle, rhythmic pulses that could betray the presence of binary black holes dancing in the dark. This vast survey will provide the context, showing us not just individual quasars, but their place in the grand tapestry of cosmic evolution. Then there is the Square Kilometre Array, a radio telescope of almost unimaginable sensitivity. When its thousands of antennas across 2 continents are linked together, it will form a single eye as large as a continent, capable of seeing the faintest whispers from the early universe. It could directly trace the flow of gas fueling the first supermassive black holes and map the magnetic fields that sculpt their colossal jets with exquisite detail. Together, these observatories offer the tantalizing possibility of a direct image of a supermassive black hole's event horizon, not in our calm galactic center, but in the furious heart of an active galaxy. We would see the shadow of the abyss itself, set against the brilliant, swirling backdrop of its own accretion disk. This is the future of quasar research, a coordinated assault on the greatest mysteries of the cosmos. These new eyes on the sky promise to finally answer how these monsters are born, how they grow, and how they ultimately dictate the fate of everything around them. From the illusion of faster-than-light motion to the cosmic echoes of reverberation mapping, each of these 25 phenomena reveals a universe far stranger and more dynamic than we ever dreamed. Quasars are not merely distant points of light, they are fundamental laboratories testing the laws of physics under conditions of gravity, temperature, and density that we could never hope to recreate on Earth. They are the key that unlocks our understanding of how supermassive black holes are born, how they grow, and how they ultimately command the evolution of the galaxies they inhabit, shaping the very large-scale structure of the cosmos. Every flicker of their light, every warp in their spectrum tells a part of this grand story. We have traveled from the event horizon to the edge of the observable universe, all by studying these brilliant, furious hearts. So tell me, which of these bizarre phenomena reshaped your view of reality the most? Was it the cosmic chameleons that changed their look, or the ghostly dark galaxies revealed only by a quasar's flashlight? Let me know in the comments and subscribe to continue exploring the universe's greatest mysteries together.